today we're going to do section 6, and that is limits of sequences. So we've looked at sequences, we've written them out, we've added them up. Those are series, right? But now what we're going to look at is what do they go to as n gets larger and larger? Are the terms going to a certain number? So if we look at, let's look at the sequence where the general term is 1 over n. And if we write out the first 6 terms of this sequence, it's when n is 1, you got 1. When n is 2, you got 1/2, and then 1/3, and then 1/4. And hopefully you see, like, these guys are definitely getting smaller as you're going along, right? But maybe it's not super obvious. So let's look at bigger numbers. Let's plug in, how about when n is 10? Well, when n is 10, you'd have 1 over 10, which in decimal form would be 0.1. Let's look at it even bigger. How about the 100th term? Well, that would be 1 over 100. And in decimals, that's 0.01. Let's go even bigger than that. How about the 100,000th term? So 1 divided by 100,000 would be 0.00001. And so I don't know if you, hopefully you see it, that as you're getting larger and larger, which is what we're talking about, as n gets really, really large, like when n is infinity, right, which is way larger than 100,000, right, then what's happening to each of these terms? And they're definitely getting closer and closer to 0. And so what we say, this is limit notation. We are prepping you for calculus next year. Whoop, whoop. The limit as n goes to infinity of 1 over n, we say that it's equal to 0, because as n gets super duper large, the 1 divided by a very large number ends up being 0. Now, super important that there is no term that is actually equal to 0, right? Dividing by, 1 on top, you'll never equal 0, but it's just getting super duper close. It's approaching that asymptote, right? It's getting really, really close, not touching that asymptote, but getting really, really close. So that's why it's never actually equal to 0, but like 1 over n is there's not a value you can plug into n to where it's actually equal to 0, but it gets so close that we could say that the limit is equal to 0. All right, so to find the limit of a sequence, we usually have to algebraically manipulate it. So for example, let's find the limit of the sequence as n increases without bound. That's saying, like, find that limit as n goes to infinity. So what about if the nth term is 2n plus 8 over n? So here's this algebraic manipulation. That's the little trick, is I'm going to divide by what's in the numerator. I'm going to divide by the variable in the numerator. And if there's more than one, I'm going to divide by the variable in the, I said numerator, I meant denominator, the bottom guy. I'm going to divide by whatever is the variable with the highest power. So there's only one here, there's only n, so I'm going to divide the top and the bottom by n. Divide the numerator by n, divide the denominator by n also, because I can talk. Yes. All right, so what happens? Well, you would have a 2n divided by n plus 8 over n, boop, boop, boop. And on the bottom, you'd have n divided by n. All right, so let's simplify this. 2n divided by n, those n's will cancel. You'll be left with a 2. I still have an 8 over n here. That didn't simplify. But n over n is a 1. So you end up with a 2 plus 8 over n all over 1. And now, when we take the limit as n goes to infinity of this manipulated guy, right? Remember that the limit from the previous slide, we had the limit as n goes to infinity of 1 over n goes to 0. Well, this is just like 8 times that. So that whole thing goes to 0. The limit is of 8 over n as n goes to infinity, that goes to 0. And so you're left with 2 plus 0 over 1, which is 2. And limits. Pretty snazzy, huh? Let's look at another one. So this time it's just not an n, it's an n squared. both top and bottom, right? Um, I'm going to divide by the n squared, both, and I'm going to divide it by top and bottom by n squared. You'll have an n squared over n squared plus 5 over n squared on top. And on the bottom, you'll have 3n squared divided by n squared. The n squareds here will cancel. You'll be left with a 1 plus 5 over n squared. That didn't simplify. And then 3n squared over n squared ends up with a 3. And now when we take the limit as n goes to infinity of this guy, 5 over n squared. We know 1 over n goes to 0. Well, 1 over n squared goes even faster to 0. So, and then 5 times that is still 0. So um, you're left with a 1 plus 0 over 3, which ends up as a 1/3. There we go. Easy peasy lemon squeezy, right? I know it's not. It's this notation that's like so scary. I just want to point out that the rules for horizontal asymptotes, if you remember those, you probably don't. I'll refresh your memory right now. When the degree on top was the same as the degree on the bottom, do you remember that you took that that horizontal asymptote was y equals the leading coefficients, 2 over 1, not a coinky dink. Over here, you got an n squared over n squared. Same degree. Degree on top, same as the degree on the bottom. Your leading coefficient, 1 over 3. Not a coinky dink. It's the same thing. Your horizontal asymptote is kind of giving you what the limit would be if it was a function. Yeah, if that makes sense. But so yeah, this is the work involved to show why it is that way, but it will always be that when the degree on top of the variable is the exact same as the degree on the bottom, your limit will be the leading coefficients on those on just the variables that have the same degree. All right. If a sequence gets closer to a number, we call it big L, that's the limit. As n increases without bound, it is said to converge, and we call it a convergent sequence. So if there is a limit, right, as n goes to infinity, it says we say it converges. If it doesn't converge, we say that the sequence is said to diverge, or it's divergent. If it does diverge, there's lots of ways it can happen. It might just be getting larger and larger. The terms are getting larger and larger. Another way that it can happen is if your numbers are going like positive, negative, positive, negative, positive, negative, things like that, then positive, negative, but also getting larger. If they're getting smaller and closer to the x-axis, then that's something different. But if you're going from 1, -1, 1, -1, 1, -1, right, then that we say it oscillates. Okay. Or if you think about, sine and cosine, right? Both sine and cosine, as your x is going to infinity, which value do we choose, right? Those graphs are total oscillating graphs. They're going up and down. So we can't do those either. Or they don't converge to a specific number as n goes to infinity. Okay, let's look at another example. We're going to find the first 5 terms and decide if the sequence converges or diverges. So how about the square root of n? So let's write out the first 5 terms, right? The first term would be the square root of 1, which is 1. Second term would be rad 2. Third term would be rad 3. Fourth term would be rad 4, which is just 2. Fifth term would be rad 5. That's all they want me to find. So you could get these decimal approximations, right? But hopefully you see that these are getting larger slowly, but they are getting larger. And so we say that this guy diverges. It's not approaching a specific number as n goes to infinity, right? When n is 100, your answer is 10. And when your answer is, what would it be, 10,000, your answer is 100. Like it just keeps getting larger and larger. How about this guy? En is n cubed over n cubed plus 1 over 2n squared minus n. All right, so here, the degrees do not match. So you can't say the answer won't be 1/2. I'll tell you that much, right? Because your the degree on top is bigger than the degree on the bottom. I don't know if you remember the horizontal asymptote rules, but when it was bigger on top than on bottom, there was a, I'll tell you at the end. Okay, so what are we going to do on this? Well, let's write out the first 5 terms first. When you plug in a 1, you'd get 1 cubed plus 1 over 2 minus 1, so you get 2. The next one would be 9 over 6. When you plug a 2 in, it's 2 cubed is 8, 2 squared is 4, and then times 2, and then minus 2, which is about 1.5. When you plug in a 3, you'd get 27 plus 1, and then 2 times 9 minus 3, so 28 over 15, which is about 1.87. Plugging in a 4 into n, 4 cubed is 64, and then plus 1. And then 2 times 16 would be 32, minus 4 would give you 28, so that's about 2.3. The next one would be 125 plus 1, and then 50 minus 5. So 45, you get 2.8. So you started at 2. It kind of went down at first, but then it starts increasing again. And so this guy definitely diverges. So back to what I said about degree on top bigger than the degree on the bottom. If you remember your horizontal asymptote rules, when the degree on top was bigger than the degree on the bottom, there was no horizontal asymptote, meaning there's no limit happening to as n goes to infinity. So horizontal asymptote rules still match up with what this is too. You also could have done my trick of, from the last slide of if you divide top and bottom by n squared is what I would do, because that's the highest degree on the bottom. And you would end up having, you're taking the limit of n as n goes to infinity, and that's infinity. So it diverges. All right. Let's determine whether these geometric, you know what geometric means. We're multiplying by the same thing to get to the next term, right? Determine whether these geometric sequences converge or diverge. So negative 10 to the nth power. Well, let's think about it. Your first term would be negative 10. Second term would be positive 100. Third term would be negative 1,000. Fourth term would be positive 10,000. Yeah, diverges. It's oscillating and getting larger and larger away from 0 as it's going down the line. How about 5 to the power of n? Well, when n is 1, you'd have 5. When n is 2, you'd have 5 squared, so 25. 5 cubed, 125. 5 to the 4th is 625. It just keeps getting larger, larger, larger. Diverges. Oh, 1/4 to the n. When n is 1, you'd have 1/4. And when n is 2, you'd have 1 over 16. When n is 3, 1 over 64. So they're getting smaller, right? When the denominator is becoming a bigger number, then the whole fraction is becoming smaller. So that one converges. How about negative 1/4 to the nth power? All right, so here's a trickier one, right? Because I warned you, oscillating, but also getting bigger as you're going along. So here, you got a negative 1 over 4. When you plug in a 1, you'd have negative 1/4. Plug in a 2, positive 1 over 16. Plug in a 3, negative 1 over 64. Plug in a 4, right? You keep on going. This guy converges, and the reason why it converges, so even though it's going positive, negative, they're getting closer and closer to the x-axis with each time you plug in another exponent. Yeah, the whole fraction itself. It may be bouncing back and forth, like above the x-axis, above, below, but each time it's bouncing and it's getting closer to the x-axis, so it'll converge to 0. All right. Can you generalize these geometric sequences and make a rule for what will converge or diverge? Can you tell? You've learned it before. Geometric sequences. Yeah, because these are like infinite sequences. Do you remember the sum of a geometric series. Yeah. You can only find the sum when r was less than 1. So for these two, here your r is -10. Here your r is 5, right? Because you're multiplying by 5 each time. Here, this one, your r was 1/4. And this one, your common ratio is -1/4. This is if you were to list them all out with commas in between. So can you make the rule for what will converge and diverge? If the absolute value is less than 1, it converges. And when the absolute value is greater than or equal to 1, it diverges. Well, when it's equal to 1, it's not even a geometric sequence because it's just 1, 1, 1. So let's get rid of that. No, it's not a geometric sequence if it's just a 1. All right, so hopefully you remember those rules, right? We could find the sum of a geometric series when your r, the absolute value of r. It doesn't matter if it's negative or positive, right? It converges. All right, try these guys on your own. So pause the video right here. And what I want you to do for each of them is characterize each sequence as convergent or divergent. And if it converges, give the limit. Highly recommend that you maybe write out a few terms. Yeah, that might help you. Otherwise, use the tricks I used. Pause the video right here. All right. Hopefully you paused it, tried it at least, give some thought to it. What happens here? Well, as the limit as n goes to infinity of 1 over n will go to 0. And so you end up with just the square root of 9 minus 0. And so it is convergent because the limit as n goes to infinity is just 3. This guy, highly recommended. I gave you the hint of you should write out a few terms, right? If your sequence is 7, first term, 7. Second term, 7. Third term, 7. Fourth term, 7. 7, 7, 7, right? And so is it convergent? Yeah, no matter what n is, as n goes to infinity, the value of the sequence will end up being 7. So that is convergent. I kind of gave you the hint before about the n cubed over n squared. Degree on top is bigger. I'm expecting this to be divergent. I do show it in work. I'm going to divide top and bottom by n squared because that's the highest degree in the denominator. And when you do, you'll take the limit as n goes to infinity of, I've got each of the terms divided by n squared. So this guy right here becomes an n. This guy zeroes out because it's 1 over n. This is 4 over n squared. That'll zero out also. N squared over n squared is 1. And then 1 over n squared zeroes out. So you end up taking the limit of n over 1 as n is going to infinity. Infinity it is. And so this guy is divergent. All right, hopefully that all made sense. If not, come see me in office hours. This is all a really super important stuff for taking calculus next year, whether you're in college or with us. You're going to be learning all of this for sure. All right, I hope you all are having a fantabulous day. Ta ta.